Hello everyone, and welcome to my presentation. Today I'll be presenting my work in my PhD towards isotropic plasma atomic layer etching. Very grateful for this opportunity to present my work, as well as for being nominated for this award. So before I go on to talk about my work on isotropic plasma atomic layer etching, I'd like to first talk a little bit about ALE more generally. So atomic layer etching is defined by its cyclic nature with self-limiting half cycles. ALE stands to be incredibly useful for the production of advanced integrated circuit devices, such as thin field effect transistors and gate-all-around field effect transistors. The gate-all-around field effect transistor quite nicely illustrates that we will need both anisotropic ALE and isotropic ALE to achieve these complex devices. Anisotropic to define the fins, and isotropic to define the nanowires. So if we look at ALE more generally, and we look at our ALE database that myself and our group at Eindhoven curates, and when we look at our ALE database, we can see that the processes are mostly split into anisotropic plasma ALE and thermal isotropic ALE, these top left and bottom right quadrant here. And we can see that after being introduced in about 1988, the number of publications for ALE has been slowly increasing, and the number of materials that can be etched by ALE is also slowly increasing. This suggests that there's kind of an increasing demand for this atomic scale processing. We also noticed that isotropic ALE is first documented in about 2015 by the George Group. And some of you may be asking, what about this region in the bottom left here and this region in the top right? So this bottom left region of anisotropic thermal ALE, we don't think will be particularly feasible, as thermal reactants tend not to be directional. This therefore just leaves us with plasma isotropic ALE as a possible avenue to research. We suspect, so this is the question we want to answer with our research, is can plasmas be used for isotropic ALE? So this is a largely unexplored region so far, and we want to try and shine a light on this more generally. So we also expect that plasmas may offer some merits to processing. So similar to the pathway that's been shown by plasma ALD, we suspect that by using a plasma for our reactions, the increased reactivity of the plasma radicals over conventional thermal ALE reactants will allow for an increase in etch per cycle, as well as allowing us an ability to operate in a wider temperature window at these lower temperatures. So when it came to developing an isotropic plasma atomic layer etch process, we first looked towards the conventional thermal ALE literature. And with one of the most documented processes in the thermal ALE literature being the etching of aluminium oxide by hydrogen fluoride and TMA. In half cycle A of this process, the surface is fluorinated by hydrogen fluoride, creating this self-limiting aluminium fluoride layer. This region the formation of this is self-limiting, as this aluminium fluoride acts as a diffusion barrier and prevents further fluorination of the bulk underneath. Etching is then achieved in this process in half cycle B by dosing TMA, which performs a ligand exchange reaction with the aluminium fluoride surface, generating volatile dimethyl aluminium fluoride. This allows for etching of the film to be achieved and is also self-limiting, as once it reaches the bulk aluminium oxide underneath, it no longer etches away the material. It was noted that this process chemistry can be used both for aluminium oxide etching, but also for aluminium fluoride deposition. Now this interested us because recently, within our group, we have developed an aluminium fluoride plasma ALD process using SF6 plasma and TMA. This was shown to follow a very similar reaction chemistry to the aluminium fluoride thermal ALD, and led us to question whether we could develop an aluminium oxide etch process using this SF6 plasma TMA process. So the first question we want to answer is, what is the reaction mechanism for an ALE process using SF6 plasma and TMA? And to investigate this, we used FTIR Fourier transform infrared spectroscopy measurements. And at the bottom left, you can see the process we used for these reactions. So the first step was an SF6 plasma, followed by a pump, a TMA dose, and then another pump. So we first look at the figure on the left here. We can see the aluminium oxygen bond absorbance region. So this is absorbance spectra taken after each full ALE cycle and reference to the as deposited film. We can see that with increasing number of ALE cycles, there is a decrease in the aluminium oxide absorbance band. This would suggest that we are seeing removal of aluminium oxide from the substrate surface. If we then look at the FTR, the absorbance spectra for each half cycle referenced to the previous half cycle, we can see that when dosing TMA, so this blue line here, we see that when dosing TMA, there is an increase in methyl group absorbance. This is thought to be due to once the TMA has removed the aluminium fluoride surface region, it is then free to react with the exposed aluminium oxide bulk underneath. So this absorbed TMA generates a methylated surface. In the following SF6 plasma exposure, we see that there is an elimination of these methyl groups. We think this is performed by fluorine radicals, which also fluorinate the aluminium oxide surface. So taking these observations, and also the similar observations that have been seen for thermal ALE, we think that we are seeing a fluorination and ligand exchange reaction mechanism for our SF6 plasma TMA process, with the key difference between this process and the thermal process being the use of plasma radicals as opposed to hydrogen fluoride to modify the initial aluminium oxide surface. Etching is then achieved in a similar manner by using TMA. So an important aspect of any ALE process is the saturation curves of both reactants to show that the process can be highly controllable. So before I talk about that, I'll briefly outline the reactor we used for this process. So on the left here, you can see a diagram of the home-built reactor that is equipped with an inductively coupled plasma source and some in situ diagnostics. On the right here, we can see a schematic of the process we used for these experiments, which in half cycle A involves an SF6 plasma and pump step. And then in half cycle B, there is a TMA dose and then a TMA hold step. The hold step is used to maximize exposure of the TMA to the substrate. And then the gate valves are opened before pumping of the reactants occurs. So as I alluded to, the first parameter of our ALE process that we checked was the saturation curves, which we can see here. We see that for these reactants, we see typical ALE behavior for a fluorination and ligand exchange reaction mechanism. And if we look a bit more closely at the SF6 plasma saturation curve on the left here, we can see that this obeys a quasi-saturation behavior. This is expected of a fluorination reaction because of the diffusion-driven nature of the fluorination. So as I mentioned for the thermal ALE, there's that aluminium fluoride diffusion barrier, which we think we have here. That's the formation of that allows the self-limiting behavior. So the SF6 plasma exhibits quasi-saturation behavior. However, for the TMA dose, we see much better saturation behavior. So from these diagrams, we can conclude that we can use these reactants for ALE processing. To further show the synergy of our reactants, we performed an experiment similar to the famous Coburn and Winters experiment, where when only exposing the substrate to half cycle A, we have a constant thickness, and when only exposing the substrate to half cycle B, we have a constant thickness. However, when we expose the substrate to alternating AB half cycles, we see that there is a linear dependence between number of cycles and etch depth, implying this is an ALE process. If we now look a little bit more closely at our film thickness, we can see that when only dosing SF6 plasma, we see that there is a small thickness increase. This is in agreement with the formation of a thin fluorinated surface and is in agreement with thermal ALE. When we switch from just dosing SF6 plasma to just dosing TMA, there is an initial 3 angstrom decrease in film thickness, after which film thickness remains constant for the following pulses. This kind of behavior further supports the fluorination and ligand exchange reaction mechanism we previously proposed. If we now evaluate the synergy of our process using the etch per cycle obtained in half cycle A and half cycle B compared to the full ALE etch per cycle, we can see that our SF6 plasma TMA process exhibits near 100% synergy. It was also noted that this process could be used for etching of hafnium oxide. Unfortunately, we weren't able to fully investigate this process, but we believe that it will show ALE behavior, as etching is not observed when only dosing half cycle A or B, but can be observed when dosing alternating AB half cycles. It was also noted that the etch per cycle we achieved here was higher than a comparable thermal ALE etch per cycle using hydrogen fluoride and TMA. We hope once coronavirus is over, we'll be able to go back into the lab and finish off this experiment. So some of you may be wondering how we can say that this plasma process is isotropic, as more generally plasmas are used for anisotropic ALE. So to test this, we use patterned silicon substrates coated in aluminium oxide by plasma ALD. A figure of one can be seen on the left here. We then expose these test structures to 40 ALE cycles, as can be seen in the figure here. We can see that the film is removed over the entire trench structure, and that the smooth conformal film is maintained over the entire trench structure. If we evaluate the etch rate, we can see that it's consistent over the entire trench structure, which would suggest that there is a negligible contribution from the anisotropic directional ions in the plasma towards etching. So this yields a net rate of about 2.9 angstrom per cycle, which when compared to our plain ALE substrate, etch per cycle, is very similar. So if we think back to my first slide, where the initial research question was, can plasmas be used for isotropic atomic layer etching? This data set, as well as the saturation curves, would seem to suggest that yes, we can use plasmas for isotropic atomic layer etching. To provide some comparison between our work and current thermal ALE work, we evaluated the etch per cycle as a function of substrate temperature, and we observed that for increasing substrate temperature, there was an increasing etch per cycle. We also noted that there was a transition from ALE, so a positive etch per cycle, to ALD occurring at low temperatures. So this negative etch per cycle here denotes growth. This transition occurs at about 150 degrees C, substrate temperature. So if we now compare our ALE etch per cycle to that of conventional thermal ALE using hydrogen fluoride and TMA, we can see that there are some merits possible from using a plasma ALE process. These merits can be the higher etch per cycle, which we observe over the entire substrate temperature range we investigated, as well as the ability to etch at lower temperatures than have previously been shown in the literature. So if we think back again to the first slide I showed, this is very similar to the benefits we expected based on previous work towards plasma ALD compared to thermal ALD. So that brings me towards the conclusions of our work. And we can see that so far we have proved that isotropic plasma ALE is possible via a fluorinating plasma in TMA. We used SF6 in our process, however we expect that any fluorine-containing plasma could be used for the fluorination step. We also think we've further established isotropic plasma ALE as a viable research direction and as an alternative to thermal ALE, and we hope that this will help encourage others to further investigate this avenue of research. We've also shown, so not only have we shown that plasma ALE is possible, we've shown that the plasma ALE isotropic process can offer some benefits, namely in the higher etch per cycle and the lower operating temperatures that it allows. This is analogous to very similar plasma ALD work. So this was just the beginning of my PhD project, and looking forward, we want to further investigate the SF6 plasma TMA process, but also to investigate and develop new isotropic plasma ALE chemistries, as we think this will expand the toolbox of ALE more generally and help advance plasma processing. Thank you very much for your attention.